Ladies and gentlemen, dear colleagues and guests, my name is Serbian Society, and on behalf of our society and our hosts, I wish you a warm welcome to the opening ceremony of the 10th International Congress of the Serbian Society of Mechanics. This year, hosts of the Congress are the Faculty of Mechanical Engineering and the Faculty of Civil Engineering of the University of Niš. It is co-organized by the Mathematical Institute of Serbian Academy of Sciences and Arts and the Faculty of Mechanical Engineering of the University of Belgrade. As an introduction, I would like to present a brief retrospective of the mechanics in Serbia. At first, at the Great School in Belgrade, which was the 19th century predecessor of the University of Belgrade, mechanics became a regular part of the university curriculum. First deep traces were laid by Professor Ljubomir Klerić, mining engineer, who taught mechanics as a university subject and wrote the first university textbook on theoretical mechanics. Expansion of the University of Belgrade in the first half of the 20th century led to the development of mechanics in engineering, physical and mathematical community alike. We may proudly mention Professor Milutin Milankovic, one of the greatest scientific minds that we had, who was professor of mechanics at the University of Belgrade. Intensive development of science and technology and expanding of higher education after the Second World War stimulated university professors and scientists to organize the first Yugoslav Congress of Rational and Applied Mechanics, which took place in Bled, nowadays Slovenia, in 1952. At the Second Yugoslav Congress of Theoretical and Applied Mechanics, held in 1954 at the same place, Yugoslav Society of Mechanics was officially established. Since then, congresses have been held biennially at different places or all over former Yugoslavia. Since it was established, Yugoslav Society of Mechanics was an adhering organization of the International Union of Theoretical and Applied Mechanics. The Serbian Society of Mechanics, as its successor, kept the same status in IUTM. International activities were reflected through the organization of two GAM congresses in 1985 in Dubrovnik and in 2013 in Novi Sad, and two Euromech colloquia, 214 in 1986 in Kupari, and 650 to be held this year in August in Belgrade. Changes of political circumstances during the 90s implied new organization of the congresses. Since 2007, they were organized as international congresses of the Serbian Society of Mechanics. They continued to bring together leading academic scientists, researchers and scholars who shared their experiences and research results in various fields of theoretical and applied mechanics. This year, we are gathering in the beautiful town of Niš at the 10th International Congress of the Serbian Society of Mechanics. And it is my pleasure to invite Professor Vladimir Stojanovic, President of the Organizing Committee, to address the audience.
Thank you very much, Professor Simic. Ladies and gentlemen, honored plenary speakers, respected professors, colleagues, dear valued partners, and dear friends. Welcome to Niš and to the 10th International Congress of the Serbian Society of Mechanics. It's my great honor to warmly greet you on behalf of the organizing committee, the Faculty of Mechanical Engineering and the Faculty of Civil Engineering and Architecture at this Jubilee gathering. Above all, I wish to express from the depth of my heart gratitude to the plenary speakers who graciously accepted my personal invitation to take part in this conference and who have come to us from across the Atlantic. My dear Professor Reddy and my dear Professor Lishakov, thank you. From the United States, my close collaborator, dear Professor Deng from Canada, and from Western Europe, my dear Professor Kinslow. I owe my immeasurable thanks to Professor Gonçalves from Brazil, Professor Goryacha from Russia, and Professor Knežević, Serbian-born scientist working in the United States, for honoring us with your presence. Niš, the city of Emperor Constantine, a crossroads of cultures and ideas for more than 2,000 years, is once again the host of our Congress, exactly 30 years after it was last held here. In going so, we are not only reviving tradition, but also reaffirming our enduring dedication to excellence, innovation, and international cooperation in the field of mechanics and related disciplines. Since their founding in 1960, the Faculty of Mechanical Engineering and the Faculty of Civil Engineering and Architecture have grown into respected European institutions. Their development has been guided by the enhancement of teaching and research quality, the recognition and support of young talents, the promotion of multidisciplinary projects, and increasingly intensive international mobility. This year's Congress brings together 258 authors and co-authors who have contributed to 88 scientific papers, along with 7 outstanding plenary lectures that will enrich our program with cutting-edge insights and research. A cherished tradition of our society is the Rastko Stojanovic Award, established in 1974 to honor outstanding contributions in mechanics. Over the years, nearly 60 young researchers have been honored with this award, and we are especially pleased that many of them are present with us today. This year, we are proud to announce 2 new laureates who will present their work in today's plenary session. I would especially like to highlight the Chair of Mechanics at the Faculty of Mechanical Engineering, whose past and ongoing achievements and international collaborations have been crucial to the organization of this Congress. In that spirit, I would like to extend my warmest and most heartfelt thanks to all members of the Chair who are also part of the organizing committee, as well as to all members of the organizing committee from the Faculty of Civil Engineering and Architecture. Without your enthusiasm, this event could not have been realized. My sincere thanks to all of you. I also wish to express my special thanks to the reviewers who, despite short deadlines, contributed greatly to the scientific quality of the proceedings. Our partners from industry and governmental institutions whose support has given this Congress additional value, and our volunteers and students whose enthusiasm ensures that everything runs flawlessly. Last but certainly not least, in fact, most importantly, throughout the entire year of conference preparation, the person who stood by my side as my right hand in all technical and non-technical matters was the co-chair of the organizing committee, Professor Juliana Simonovic. My gratitude goes to her for all the reminders and, to be honest, for helping me with many things I wouldn't have known how to do on my own. I wish you all an inspiring Congress, fruitful discussions, and above all that you enjoy the warm hospitality of Niš. Let us celebrate this milestone together, honoring both of history and the promising future mechanics research in Serbia and beyond. Thank you very much.
Thank you, Professor Stojanovic. The opening ceremony and the first part of today's program are held in the pleasant and stimulating environment.
And to have the opportunity to address the audience. I wish to thank the Faculty of Mechanical Engineering, the Dean Janevski and his team, for recognizing the importance of institutional cooperation in our innovation ecosystem, including organization of this kind of conferences within the Science and Technology Park Niš. Science and Technology Park Niš is founded by Republic of Serbia, City of Niš and the University of Niš. So I wish also to welcome you all on behalf of our founders, City of Niš, University of Niš and Ministry of Science and Technological Development of Republic of Serbia. When we speak about Niš and innovation ecosystem, we usually recall on electronic industry in Niš, which was leading the industry within the 20th century. Unfortunately, most of people forgot that industrial development in Niš actually started at the end of the 19th century when the railway between Belgrade and Niš was finished, and due to that fact, mechanical engineering industry was founded in Niš, and actually it started the industrial revolution here in the city. Afterwards, we had the electronic industry, and we were recognized as an engineering hub for this part of Europe, I would say also for this part of the world. Nowadays, with the establishment of Science and Technology Park Niš as an institution which is trying to facilitate reconstruction, I would say like that, of the innovation ecosystem in the region, together with the faculties from the University of Niš and successful companies which are operating in our region, we are trying to boost further development of innovation ecosystem. So at this moment we are hosting around more than 70 companies within Science and Technology Park Niš, out of which more than 50 are startups founded within the last couple of years, and with the support and involvement of our distinguished researchers from the university, we truly believe that in the future this trend will continue, and we will be able to try to recall the City of Niš as an engineering hub again. I would not like to waste your time anymore. On behalf of the Science and Technology Park and especially City of Niš, I wish you a successful conference and a pleasant stay in our city. Thank you.
Throughout the years, activities of the Serbian Society of Mechanics were recognized and supported by the Ministry of Science, Technological Development and Innovation of the Republic of Serbia. We are grateful for that support, and I have a pleasure to convey you the best wishes from the Minister, Academician Bela Balint. Also, scientific activities in the field of mechanics are organized in the frame of research projects which are financially supported by the Science Fund of the Republic of Serbia. Currently, several projects are funded within different calls. Director of the Science Fund, Professor Nenad Filipovic, who is also former president of the Serbian Society of Mechanics, wishes us successful Congress. As you realized at the beginning of the opening ceremony, we have a nice musical program today, thanks to the academic choir of the Student Cultural Center of Niš, conducted by Mrs. Ivana Mirovic. In the next section, we will have an opportunity to like to thank again for this beautiful musical program. And we are coming to an important part of this opening ceremony, because this year we are also celebrating one remarkable jubilee. In 1975, publishing of the journal Theoretical and Applied Mechanics, official journal of Yugoslav and later on Serbian Society of Mechanics, commenced. Therefore, it is the right time and the right place to invite Dr. Vladimir Dragovic, Editor-in-Chief of Journal Theoretical and Applied Mechanics, to shed light on the history and the future of the journal.
Professor Simic, esteemed colleagues, it is my great pleasure to address you on behalf of our journal, Theoretical and Applied Mechanics, on this humble anniversary, 50th anniversary. We just hope that we are halfway through. So, as Professor Simic said, it started in 1975. It is currently published by Mathematical Institute of Serbian Academy of Sciences and Arts and Serbian Society of Mechanics. This year it was recognized by Serbian Ministry of Science. This is important for domestic authors as category M23. And we are especially proud of our policy that our journal is free of charge for authors and also free of charge for readers. So it's open in this nice sense. So it's not it's a non-profit pursuit, and of course this is thanks to our generous sponsor, Ministry in charge of Science and Technological Development and Innovation. So since 2015 I have a pleasure to be Editor-in-Chief, and I would like to use now on 10th anniversary to specifically thank Božidar Jovanović as Deputy Editor-in-Chief, Borislav Gajić as Secretary, who is present here, and our technical editor, Dragan Achimović. And here are the members of our editorial board. So you see here people from various countries and of course around this region. So we have very efficient and very hard-working editorial board, and very efficient and referees process. So I would like to thank the members of the editorial board for their hard work. So let's go back to the history. So 1975. In this nice opening of Professor Simic, you could have recalled once again how many things has changed since 1975, in this region especially. But Theoretical and Applied Mechanics managed to be published year after year, maintaining and, as much as we can, improving its scientific content. So the journal was established thanks to leadership wisdom of late Professor Veljko Vučić, who served as the founding editor, and then this torch of editing was carried out by Professors Teodor Atanasković and Đorđe Đukić, and then Milan Mićunović. So let's thank our previous editors-in-chief for this tremendous work over decades. So here is, of course, we are trying to be intact with modern ways of presentation. I told you this is a free of charge for authors and for readers. We have all our previous issues maintained online, so you have a free access to all of them. And here is again one piece of history. Here you see the first editorial board from 1975. At that time it was, as Professor Simic said, it was published jointly by Yugoslav Society of Mechanics and Mathematical Institute of Serbian Academy of Sciences and Arts. So in 1975, that was this is the first volume, the first issue. And just 50 years later, we have this Jubilee volume, and here is the list of authors who contributed to this year's volume. So, in hard copy, our journal looks like this. And once again, here are the basic things, the basic data, and this is also our cordial invitation to all of you, to all members of Serbian Society of Mechanics, to all scientists in the field of mechanics around the world, to our plenary lecturers, and to all participants of this Congress. Please submit your manuscript to theoretical and applied mechanics. Only nice and excellent contributions from our potential authors can guarantee that we can, in the future, be on the level that we are now, and we also always strive to be better and better. So once again, please submit your best manuscripts to theoretical and applied mechanics. We will do our best that your manuscripts get rigorous referee review and to be published soon once it reaches the high standards of our journal. Thank you very much.
Thank you, Dr. Dragovic. I'd like to also express our gratitude to the sponsors of the Congress, Prager Electronic from Volkersdorf, Austria, Dantec Dynamics from Skovlunde, Denmark, Dantec Spajic Company from Negotin, Serbia, and Elixir Prahovo from Prahovo, Serbia. As a final remark, I would like to draw your attention on 3 plenary lectures that will take place at this hall. And after the lunch break, we shall have a plenary session for the candidates for Rastko Stojanovic Award for Young Scientists. It is my very great pleasure to announce the 10th International Congress of the Serbian Society of Mechanics officially open. Thank you very much.
Ladies and gentlemen, esteemed colleagues and distinguished guests, it's with sincere excitement and profound respect that I have the honor to introducing today's plenary speaker, Professor J.N. Reddy, who joins us from across the Atlantic from the state of Texas. Professor Reddy is Distinguished Professor in Mechanical Engineering at Texas A&M University. His remarkable academic career spans the authorship of more than 25 textbooks and over 800 scientific articles, placing him among the most highly cited researchers in the field of modern applied mechanics. For these pioneering contributions to shared deformation theories, the development of locking free shell finite elements, and non-local continuum models, he has received the Timoshenko Medal in 2019 and the ASME Medal in 2016, the highest honors awarded by the American Society of Mechanical Engineers. The subject of today's lecture reflects Professor Reddy's development of robust locking free shell finite element for a large deformation analysis of laminated and functionally graded structures and non-local approaches for modeling architectural materials and fracturing brittle solids. These advanced methodologies, developed in close collaboration with his colleagues, offer engineers analytical tools that preserve the accuracy of full three-dimensional models while significantly improving computational efficiency. Professor Reddy is known not only for the depth of impact of his scientific work, but also for his exceptional charisma and dedication to the transmission of knowledge. His students and collaborators across the globe often speak of the boundless energy with which he inspires new generations of researchers. Today, through his plenary lecture entitled Robust Shell Finite Element and Non-Local Approach in Mechanics, Professor Reddy will guide us into the future of engineering analysis, from missingly slender composite shells to intelligent metamaterials and digital twins of structural systems. It is therefore my pleasure to invite you all to give him a warm welcome and to listen closely to the ideas that I'm confident will speak discussions through the entire Congress. Dear Professor Reddy, the floor is yours.
So, very good morning. So this is the very first trip to Serbia, and I know we have the best NBA player from Serbia. So I think now I know why Serbians are so good at both basketball and volleyball. They're all tall people, and so far it has been wonderful to visit because of the kindness of the organizers and also the great hospitality. So today I want to share 3 different topics. One is on shell elements, and second on the non-local modeling of architecture materials and structures. And third is fracture and fatigue in structures. So I will start with some comments on the computational mechanics, because that is my main area of research. I work in theoretical and applied mechanics, and computational mechanics is now a pillar by itself. When you think of for stability of structures, you need 3 legs. One is theoretical mechanics, second is experimental mechanics, and now third is computational mechanics. These 3 pillars are very, very important to advance science to technology. So I think all of you know these from all the commercial programs that we have in designing and manufacturing. So I'll say a few words about the computational mechanics role. Then I will talk about those 3 topics, close with some comments. So general remarks on computational mechanics are mostly to just tell you that, I know the journal on theoretical and applied mechanics. I think it's a great thing. Only thing we need to internationalize a bit. It is a source of pride for any country to keep mechanics, as a focus, because it is kind of dying. I'm sorry to say this, because everybody thinks mechanics is done with. All we need to do is pay attention to materials. So this is a very short sight, because mechanics is the certification of materials. You cannot use or develop materials without the help of mechanics. Mechanics is fundamental to every science, whether it's fluid mechanics, solid mechanics, heat transfer, biomechanics, anything under the sun. So mechanics has to be kept in, interest, focus, and of course funding agencies have to support it. You cannot be just thinking of using commercial programs like Abacus, ANSYS, COMSOL. That is not mechanics. It is just only application as is known yesterday, not today even. Okay? So the most important part of computational mechanics is you have to convert the mathematical models into meaningful response that we can utilize to build systems, design systems, and manufacture them, because that's where we want to go. Okay, so numerical simulations are a must because of the complexity of differential equations that govern a system or a response, because of multiple couplings, nonlinearities, geometric complexities, or simply cannot be solved by classical means. So we must use computational methods that are physics-based. It cannot be ad hoc. So it allows you to sit at the table and kind of, playfully say what if scenarios. if I change geometry slightly, if I change a material, or the response of the system, how it depends upon multiple couplings coming from various sources, with fluid mechanics coupled with heat transfer, coupled with solid mechanics. Now we have other phenomena like biological systems. So all of these cannot be solved without having the benefit of three things, as I said before. A very good understanding through observations, experiments. Second, constructing mathematical models that are based on physical understanding of the system. And third, taking them to the actual practice through computational mechanics. So that is where we have the benefit of computational mechanics, and it is really key to many developments in modern world, whether it's communication, transportation, now we are talking about medicine, biology, and so on. Okay, so I want to close by saying that there are many topics that people think they are done, just because they are in commercial codes. Okay, I am sure you're familiar with the abacus, ANSYS like, but those are really need to be improved, because the element technology in these commercial codes based on way back on old ideas, and many of them are based on human elements like turning knobs or fixing, like reduced integration, upwinding, artificial viscosity. All of these are just means to make the scheme behave. So if we understand them better, we should get rid of these artificial things. They should be all physics based. Okay? So we should not give up on these and say we should have the spirit of improving them, rather than saying, oh, that's the way it is. So I think we cannot sit on them and not pay attention to whatever little we do. Collectively we are actually advancing for the purpose of benefiting the society. So I want to just leave that message to you. Ultimately we have to benefit the society. Okay, so first topic is the shell finite element, and as you all know, it is there in any commercial that you do use in your work. My objective here is to improve the mathematical model to the extent that we can represent the actual physics more accurately. Of course, then you have to take all the way to develop computation model. Coming out of the computer is correct. So this is where we need to guard them. So those are the what you call prima donna of structures. Shell is really called prima donna of structures, right? Why? Because it is the most efficient structure. What is needed for a structure to be efficient is a curvature. Curvature goes a long way. A flat thing cannot distribute the load as efficiently as one with a curvature, and that is where the shell element. So the limitations of current one shell elements is, if most people want to use the simplest elements, lower order finite elements, meaning linear interpolation of field variables. But the linear interpolation is inconsistent with the field variables that are being modeled. If, for example, a rotation is not same degree of interpolation as a translational displacement. So, but yet people tend to use the same degree of interpolation for rotations, translations. So now, then it will have a problem of satisfying the kinematics. So they get into so-called locking, means over-stiffening of the structure. Okay? So this is where we need to spend time to understand the phenomena and remove them. Okay? So I'm going to give another example of all the conventional shell theories, both in theory as well as in finite element implementation. They do not allow thickness stretch. So they think that thickness will remain the same throughout deformation. And this cannot be true, especially if it is large deformation. So take, for example, what you see in the... Anyway, don't worry. You can see when you take a structure and stretch it, or under the loads it is going to deform. When it deforms, a thick structure will become thin. Material has to flow from the thickness, right? So that means thickness stretch is real. It is not imagined. But most important thing is, even if it doesn't change significantly, leaving it free than saying constraining the thickness. Constraining mathematically means it is transversely infinitely rigid. So this is artificially creates large stresses. Okay, so we need to bring the thickness stretch. So I'm going to just flash a expression. So I will have few mathematical expressions, but I want to mostly talk about ideas. Okay, without burdening you with too much. I know you're all well prepared to accept the mathematical expressions. So it is a displacement vector which is decomposed into in-plane, in-surface displacements, then rotations about all three normal axes, which is in the element phi. So let me see if this works. Yeah, good. So you can see this as a rotation, and then we add to that a degree of freedom, that is what I call thickness stretch. Okay, so it allows a degree of freedom, that is allowing the thickness to change. It can reduce or increase depending upon whether it's a tensile or compressive loads. So then we go on to develop the finite element interpolation, and I will just show you that a mid-surface of a shell. So one other thing that we have done that is not in the commercial code is to use what we call spectral interpolation functions, because in order to get rid of all types of thickness locking, shear locking, Poisson locking, we need to use a higher order interpolation. The reason is, again, as I mentioned a moment ago, the rotation functions and the translational displacements are not same degree of interpolation. They require different. So in order to have that, we need to go to higher order interpolation for certain variables. But we don't want to use mixed interpolation because it's computationally difficult, both in terms of meshing as well as programming. So we tend to use equal degree interpolation, but a higher order, so that we can get rid of all kinds of locking. So this picture shows the actual interpolation for different variables, and then for the instantaneous location as well as the original location, which is shown by the capital X. So we use the geometric interpolations for the geometry of shells, and that I don't want to go into too much, other than to remind you that since it's a large deformation problem, we use the green strain tensor written at the top of the screen. Here, let me show you. Yeah, right here, green strain tensor in terms of metric tensor components. And then when it comes to the strain displacement equations, because of the curvilinear nature of the shell equations, even though we start with the first order thickness interpolation, it goes all the way to the fourth degree of the thickness coordinate as shown here. So it is a question of where you want to kind of cut off. So we have tried first with the first order kinematics, that is only retain the first term through the thickness. Xi3 is a coordinate in the transverse direction to the shell. And we also used what we call 12 parameter, which is not going to be discussed here, just curiosity. Does it make any or bring additional accuracy? So we found that the expense is not justifiable for the small amount of accuracy you get with the including this quadratic term. So we neglected all of those terms in the shell theory. Okay, so the rest of the terms are just to show you the number of terms in a strain displacement equations. In terms of the constitutive model, we account for isotropic, orthotropic, and also laminated structures and functional graded structures. As you can see, material can vary through thickness from one material at the bottom to a different material at the top. So this is one of the things that in recent years we are doing is to bring the functional gradation of the material to get the effective stiffness and strength, but at the light weight. That's how the architectural materials and structures are being built. So that is really where the design is coming. As I mentioned a moment ago about the spectral interpolation functions. So the reason we need to use spectral functions because they are well behaving. They are also Lagrange interpolation functions, except the distribution of the nodes is unequal. Okay, so in the conventional case, if you have, say, some 10th degree polynomial, okay, then there would be 11 nodes in 1D, and they are equally located, but they misbehave. So mathematically speaking, interpolation functions become nearly dependent, linearly dependent, so that the coefficient matrix, such as stiffness matrix, would be ill-conditioned. So by using these unequal interpolation functions, which are shown in red color, they behave much, much better. So that's what we have done. We use even up to p equal to 8 to have the kind of kinematics that we need. Oops, sorry. Okay, so you can see the typical commercial code will have p equal to 1 and 2, linear and quadratic. But you can go to p equal to 4, p equal to 8. So as you increase the number of interpolation or degree of interpolation, one thing that you notice, there are more nodes going inside the element, right? You see a lot of nodes in the elements, and they don't speak to the neighboring elements. Only nodes speak to the neighbors or the ones that are on the boundary of the element, right? So that is another thing that we have done, is to eliminate statically all of the interior nodes and express the equations in terms of only the boundary nodes. So in the interest of time, I will only show a couple of examples. I hope it works. Sometimes, okay, it's good, it's working. Sometimes I worry. So this is a really crushing of a shell, right? So what I want you to understand is, if we take a commercial code and try to run this, it will only converge for first few load steps. Then it will get stuck. So it can't do anything. It won't converge. See, this is like really taking a shell and crushing it. And so this is not possible unless you have a higher order interpolation. See, kinematically you should have the ability to represent the geometry of deformation. So that is why we have to use p equal to 8. Okay? So we can talk about other kinds of buckling phenomena or the any kind of shear deformation. All of those are accounted through the first order kinematics. So this is another example. I want to show the importance of thickness stretch. So this is the internally pressurized cylinder. Okay, so, you think of a rubber balloon. When you take a balloon and start blowing air into it, what happens? Blows. But you can also see the color of the balloon changes because it's getting thin and thin. If you keep blowing, it will burst, because the thickness is not able to take the internal pressure anymore, right? So that means there is a thickness stretch, which is true, and I'm going to show here. Let me see if it works again. Oops, let me go back. I think Okay. So you can see the ends are held fixed, and so the internal pressure is going to make the diameter of the shell to increase. So the shell diameter will increase only by making the shell thickness change. Right? Material has to flow from somewhere to create a bigger shell. So that's what you are seeing. And so if you really plot the so this is the plot of the thickness change, delta H over the H. H is the thickness, delta H is the thickness change. So I'm putting the ratio. It can change as much as 15 or 25. I showed 25 in the scale, but it goes all the way to 20%. Okay, but this has to be large deformation. I don't want you to think that every problem will have 25%. No. Okay, so it has to be large deformation problem. All right. So we also show that stresses. This is very important. There are many graphs here, but I want to talk about one at a time. So the two most commonly used commercial program for structures are ANSYS and Abacus. So I think, market-wise, ANSYS probably has 60% of the market, and Abacus has 40%. But when it comes to structures, the percentage is reversed. Abacus is most commonly used for structures. So what you are seeing here is when the load deflection, this is the stress we are plotting at a point using the load parameter versus the stress. And so the ANSYS and Abacus results, they agree with each other. Okay? Those are the shell element results, shell element. Okay? But if you take the 3D, all right? 3D ANSYS and Abacus, 3D elements. 3D elements automatically has the stretch, correct? Because they can stretch in any direction, 3D. But shell elements in the Abacus and ANSYS cannot have the stretch in the thickness direction. So the results are quite different. Okay, in the beginning they look like same. If you look at here, in this area, but after you see large load being applied, you can see for a long way they are quite different from the results predicted by shell elements. So then you might say, oh, why don't we use just 3D elements? The problem with 3D elements is too many elements, too many degrees of freedom. Okay? So engineers are interested in getting good results with a very little effort. Right? We don't want computationally too expensive. So our thickness stretch shell element does exactly what 3D elements does. That is what you are seeing here. So our shell elements are very close to the 3D finite elements because we allowed for the thickness stretch. Okay? All right. So I think I made a case, and this is the last slide of that topic. So the 7-parameter shell element. So for that particular problem, we used 4 elements, but degrees of freedom are 2023 because it is a higher order P equal to 8, and it takes 66 CPU units to solve that problem, whereas 3D finite elements take 50,000 degrees of freedom. Okay? And 2 orders of magnitude. Abacus has a more efficient solver, only 720, but it's still a order of magnitude more effort, right? So this is very, very important because you can use shell element and get same results as a 3D finite element. All right, I close this topic and go to the architectural materials. So these days we are trying to build structures by designing the architecture. Okay, suppose you have a cantilever beam. So if you have the same material all through, you are wasting material, right? Because at the root of the structure, that's where you need the most stiffness, right? So if you use optimization, it will tell you that you are wasting material. It will come up with a taper. But you can replace the taper by designing the architecture. Okay? So there are many, many architectures you can see. But the problem with this architecture is, with real-world computation, it will take, millions and billions of degrees of freedom to model every ligament of the architecture. So what is the alternative? So we have to find some. Again, engineers are problem solvers, right? They are not just pure mathematicians. They want to solve the problems, engineering problems. So in order to reduce the computational effort, we try to find some in between. Not model every part of the structure as it is, because that would be too many degrees of freedom. And at the same time, we don't want to homogenize. If you homogenize, you lose the identity of these elements. We don't know what they are doing. If there is a buckling in one of them, you cannot predict it. So this is, I was in China last month. So I was sitting in a lounge and I saw this thing. See, nice architected structure, right? Very lightweight, okay? But it has enough strength and stiffness. You sit on it, and of course this is the coffee table in front, but the sofas are also made of the same thing. Except this seat is a little bit of cushion, just for your bottom to be not hurt. So I worked with Yoni Romanov from Finland, and so he was helping with experiments. And so what we have done is the following. So there are two possibilities. You can take a structure, architecture structure, and replace with a continuum model. But that is going to lose all the identity, because you don't know what the architecture is, other than you have effective stiffness coefficients, okay? So, and the other way is to actually replace all of those ligaments with each one by a frame model, okay, 3D space frame. So that would be more accurate, but it will be many, many degrees of freedom, because there are millions of these ligaments. So what we have done is to do the first one, but we define the theory. That means bring a point rotation. I don't know how many of you recall, our continuum mechanics, classical continuum mechanics, does not allow point to rotate. It allows the point to translate. Or 2 points connected can rotate, but a point itself cannot rotate. Okay, so this is where the micropolar theory comes in. Okay, so that's what we have done. So, and you can see a architected structure. This is where Yanni's PhD student, Ansi, he had a Marie Curie fellowship to spend 2 years with me at Texas A&M. So they also did the experiments in Finland. You can see this is a very simple architected structure with a web core, to top and bottom plates with a simple web there. So if you really exaggerate this deformation, what is happening is that web actually bends, okay, and it can even buckle, right? So how do we account for the web in a more realistic way? And that is where we brought this point rotation and were able to capture, as I will show in the next couple of slides. So what we do is take the actual architected plate, in this case a very simple sandwich structure with a web, vertical web. We take a typical unit cell and use abacus or ANSYS to get the solution at the nodes of that typical unit cell. Then we come up with the actual theory is the plate theory. But except we bring the point rotation through psi x and psi y, which is shown in the, that means we allow the rotations about the axis at a point, okay? So that, then we create a two-dimensional theory as opposed to shell type three-dimensional, and use the energy equivalence. That means energy coming from that unit cell should be same as the energy the micromorphic plate theory does. So we relate the degrees of freedom from the three-dimensional unit cell to the two-dimensional theory and calculate all the ABD matrices of a shell element. Okay, that ADGH. Or, so we cannot write an expression for them, but we can get them numerical by comparison with as I showed out the transformation on the screen. Okay, so there is a lot of detail that I'm skipping, but I gave the general idea. So if you try to run this code using two cases, where you use the 3D finite elements, shell elements, or use this micromorphic 2D theory, orders of magnitude difference in terms of computational effort. So we try to find the deflection along that line load. So the two ends are simply supported. So the deflection would be something like this. So you can see the red curve is the 2D micromorphic theory, that is ours. The blue is 3D shell finite elements. Okay? So you can see the micromorphic theory is capturing the 3D response, whereas the classical one will have as much as 20% error. Okay? And we have done this for buckling as well. And so before I get there, I'm showing you the 3D finite elements and 2D micropolar, the blue and red. So those are always very close to each other, in fact on top of each other, whereas the classical finite elements will be much in error. You can see the black one. And we plotted that with respect to the face thickness, the sandwich structure. So as the thickness increases, there is more shear deformation and more error introduced by classical plate theories. Okay, so this is, even if you try to magnify the error, it's almost that there is no error, it doesn't change. So whereas you can see the error really increases quite a bit with the face thickness increase. So this is the uniaxial compression of a plate, okay, subjected to uniaxial compression. Once again, you see the 3D and micropolar theory applied to the sandwich structure is very, very close. Here this number of half waves is shown here. So that means even higher modes of buckling are predicted much more accurately than classical theory really deteriorates with the number of half waves. And we did the similar thing for biaxial compression. Take the plate, compress in both directions. So once again you see the accuracy very good between the micropolar theory and 3D finite elements. So the third topic is fracture. So, and these are kind of, not connected to each other, but this is a very important topic because everything that you talk about, whether it's buckling, architected structures, bending, buckling, all those, ultimately we are interested in when do they fail? What is the probability of failure? What is the residual strength of the structure? What is the life of these components? So that is why fracture is a very important topic. The unfortunate issue with fracture is continuum mechanics cannot deal with fracture. I don't know how many of you closely understood that. Fracture mechanics is not a part of continuum mechanics. Okay? Because we cannot have an interior point to become a boundary point. Right? When a flaw starts and coalesces into a crack, the crack is now on the boundary. So this is the problem with continuum mechanics. So we found a way to get away from it by creating some models. All of the models have some different flaws, but I don't want to just mention without substantiating, but I will do that in a minute. So these are mostly we are spending time on brittle and quasi-brittle materials. So this is a concrete slab, okay? So, and we want to actually model the fracture in concrete. And all of you know, I'm sure, concrete, even before it is in service, it has many cracks. Just by, the way it is made, the settling takes, right? And most of the conventional approaches, they only talk about, but there are thousands of papers using XFEM, cohesive zone model, now phase field, peridynamics, but they all talk about typically couple of cracks. Most of the time one crack. Okay? So if you have many cracks, only peridynamics like one because it has the ability to capture, but all others deal with only one or two cracks. On top of it, all of them require your understanding of where the crack is going to go. That human intervention is required so that you can lay the mesh, you can lay the cohesive zone elements. So this is almost like cheating because you already know where it is going to go. That doesn't happen in real world. You don't know. Other than simple problems where you know how the self-similar crack growth takes place. So we need more robust computational technique. So that is what we are interested, and we want to develop a methodology that is not mesh dependent. You have to have certain minimum mesh. There is no question. But as you refine the mesh, it has to converge. It cannot keep changing the state of stress. Okay? So that is what we are interested. And we found, I will explain to you more idea-wise, that you have to bring non-local nature into it. Okay? And I'll explain what that non-local is. So there are two major ways that people have addressed the fracture. One is continuum-based models. Okay? So that is where the linear elastic fracture mechanics, continuum damage mechanics, XFEM, that means extended finite element, that means enrich the mesh in a certain way so that you can capture the singularity. Then second class is bond breakage models. That means you assume that any two particles connected by a bond, when that bond strength measured as a strain or stress exceeds the allowable. So that is very neat thing actually. So that is non-continuum bond breakage model. So the problem with the bond breakage is it's not coming from continuum mechanics, because continuum mechanics have saved us a lot of frustration, because it has helped us solve a lot of problems in the world, engineering problem. So it is a very nice tool. But when it comes to fracture, there is an issue. That is where we need to use continuum mechanics models, because cracks are not everywhere. There are only few places. So we should have continuum assumption in most of the system or structure, and only few places we need the fracture. So we need the both bond breakage and continuum ideas into one, and that is what this graphia is. Graph-based finite elements. There is no new finite element here. Same old, except we bring non-locality. So these are the people, colleagues we work with together with the students. Parisaf Kodabakshi from Iran. She is now a faculty member at Lehigh. So she was my first student to work on this topic. Second student, Hoyang from Korea, and he graduated 2 years ago. Now Sachin is working with me on extending what is being done by the previous two students. So I'll explain a little bit here. So the key challenges is the computational cost when it comes to, again, fracture. So in all of this, common thing is we want to have simplicity and robustness. That means we should not have these knobs and fixes that are only people who understand the problem can play with. The users are not. So they are depending on your ability to help them, make them robust enough so that they don't have to think too much. So this is where we want to reduce the computational effort. So you can see the experimental work that is done in the literature, the microplane model of Bazant, and so it takes lots of elements. You can see the 9 million elements, for example, okay, as you increase the thickness. By the way, Bazant model cannot be applied to two-dimensional structures. Even if, there is no such thing as 2D, everything is 3D in nature. But when you think of thin structure, it is basically we treat as a 2D, either using plate or shell theories, right? So the Bazant or peridynamics people cannot do it. So what peridynamics, by the way, is all non-local. There is no local. But that's not how the real world problem is. Local thing is only in few places. Okay? So, many places. Non-local is in only few places where the cracks are. So this is where we try to improve this. So I need to finish this. So only 2 slides have more mathematics. So this non-locality, the strain is defined through integral equation. What it means is strain at a point is not just only there, but it also depends on the surrounding. Okay, just think about a crack tip. It cannot propagate just because one point became weak. The region has to be weaker. That means all the points around should be weak so that it propagates. Think about that, okay? So without that, so that is where the non-locality is introduced. So RP is the diameter of the non-local region, and RP is physical variable. It is the size of the grain. So average size, okay, concrete. Okay, you can find the average concrete grain size, and that is what we use, and within that we average things. So that is where the integral equation is. Second important thing is the probability, because see, we really don't know the fracture is taking place. We only know the probability of occurring it. So that's what we bring it in here. Okay? So average survival probability is brought into the equation. So those are the 2 key things. So any point in a circular disk I'm showing, we create planes, and these planes could be any number. But in 2D, really all you need is 3. So we have done, by the way, Bazant's microplane model required 32 planes. And he doesn't have any answer why. But that's how he says it. It doesn't work unless you use 32 planes. Okay? So he was with me 2 months ago. I invited him to give a seminar to discuss the microplane model. So we created this microplane model of our own, which only required 3 in 2D and 6 in 3D. Okay? So the evolution of this survival probability is what we monitor. And then we have a rate equation for that, how it evolves also. Okay? So, we found that we need to have certain number of parameters that need to be physical. So we, including Poisson's ratio, modulus of elasticity, and the rate at which the strains evolve and strain rate effects themselves. So all of these we bring in through our non-local Graphia model. So by the way, these papers based on this work have appeared in very, very top-notch journals, Royal Society of London, JMPS, in Extreme Mechanics letters, and so on. So if you are interested, I would be happy to send you. But not only that, I will be happy to give you the program, ViewMat. That means the finite elements is not new here. What we did in terms of non-locality is new. Okay? So we created a ViewMat for Abacus. So I will be happy to give it to you, so that you run it, use it, tell us your experience and how we can help. Okay? So this is a concrete slab which is fixed at the bottom and pushed at the point where you see the 20. Okay, so let me see if I can, that's where we are pushing. So as you can expect, the crack will initiate there and propagate. It would be mixed crack growth. So the experiment, the big bandwidth, because they have to do many experiments. One experiment is you cannot just settle so that is the load deflection curve, and so you can see the solid line is based on the graphia, our work, and the broken line is phase field. So the load, as you load, they are all reasonably good, but you can see the post maximum load is not quite the same in graphia and phase field as well as experiments. So we are able to get at least slightly close to the experiment. By the way, if I really match experiment, that would be cheating because I'm only manipulating parameters. That's what I don't want to do. I want to get these parameters out with one experiment and then not change for all other experiments where you change the speed of impact or strain rate to different strain rate as long as the material is the same. Okay, that's what we do. All right. So you can see the graphia and the actual fracture, they are very, very close. Graphia is the darker line and the lighter fracture is the experiment. So we don't compare by numbers anymore. I've grown out of that, okay? As a young person, I used to compare third, fourth decimal point differences. But now I say, how close are we to the experiments? So that is what I'm doing here, okay? So graphia predicted very well with experiments. So this is, I just show you, sorry, I'm trying to run, I don't know if, okay, yeah. So you can see that, okay. So it does fairly very well. So we started doing our own experiments, simple experiments, okay, drop test on a, so you can see plaster of Paris material. So we created these discs and then use a tube to drop steel ball, okay. So you can see, and then we model using finite elements, and so you can see the top of the disc and bottom. So when it is coming from the top, actually fracture initiates at the bottom, not at the top, because of this tensile wave comes from the bottom. So you can see those are the graphia predictions. And there are experiments which also show, those are experiments from Bazant and his group. Okay? So we are able to predict very close to what is observed in experiment. By the way, there are different experiments, showed slightly different. Even experiments change. Okay? So you don't get exactly the same thing every time you do the drop test. So we were able to capture those using graphia. So this is the tracking, begins again at the bottom, and I have movie, but I don't know, yeah, so you can see, all right. So I'm going to just close this. So again, you can see on the left are the experiments, on the right are computations. We are able to predict very well in terms of qualitative understanding. Okay. So I will close this lecture by summarizing three topics. First, the higher order shell element. Higher order in terms of interpolation is necessary to get rid of all kinds of locking. Okay, so this is where the commercial codes have to change. Okay, and the second is non-local ideas to capture or represent architected materials more close to reality. Short of representing every ligament with a frame element. Okay, and graphia is the only computational thermodynamically consistent. By the way, the phase field and peridynamics, both of them exponentially growing number of publications, but yet they are thermodynamically inconsistent. I mean, you should read the critical papers by Bazant. He says these are nonsense, but nobody seems to pay attention. They keep writing the papers. So I don't understand. So did anybody think about this phase field variable? What is it? I asked people. First time as if nobody asked them. Oh, I think phi must be number of atoms. I said, what? How can phi is the number of atoms? It's some arbitrary variable. There is no physics in there, okay? They just mathematically mimicking something, okay? So it seems to predict right thing, so they say it's right, all right? Okay, so I think our objective should be realistic physics-based modeling of things, because we are not trying to sell methods. Even Graphia I'm not trying to sell. It seems to do very good. So some of you should take it and improve it and make it better. So that is what I would really like to see. So we must seek physically meaningful experiments also. So unfortunately these days most people want to do theoretical PhD. Theoretical or computational, because that's rather quick. Doing experiments is very expensive, time consuming, and it takes several years before you even start publishing. But we need them. We need those studies. Very important. Okay? So I will close by saying that our academic research, especially those who are in the universities, we have to pay attention to the long-term technological issues industry facing and try to help, work on them. See if we can help them resolve those questions. I thank you again once for inviting me, and also acknowledge the help of 3 people sitting here. Okay, so thank you for all your help. And then I will just say I had a good time last 2 days visiting different places in Belgrade. So I don't know what is this monument for, but very muscular person there holding a bird. I'm still trying to figure out. So I was able to go to this parliament even though there was protesters. So it was okay. Nobody bothered us. So thank you. I will be happy to answer any questions.
Thank you very much, Professor Reddy, for this incredible presentation. I hope that all of us were really, really excited because of your presentation. I really enjoyed in this presentation. Of course, there are a lot of things and a lot of questions from my side personally, but firstly, questions and answers. We can go. Is there somebody?
I'm going to be here, but please do ask if you have any questions now.
Yes.
Or too many things going on. But you don't have to be very specific. You can ask even generic question, how is that, or how is this, or be critical, because I have been living and sleeping with these things, so I don't have too much ego. I'll be happy to learn from your questions. So this is how it helps me go around the world, talk about what I have, and listen to others. Really, I learned a lot.
Okay, yes. Professor Knežević, also our plenary speaker. You have a microphone there. Yes.
Thank you, Professor Reddy. Thank you very much for the lecture. I enjoyed it very much. So my question is about your first subject, about the shell element. And students and I, we try to do sheet metal forming simulations, and oftentimes we would like to use shell element, but we are not sure how much we can trust it. And the regular shell in Abacus, I think everybody knows, is not so good, but they have this improved continuum shell elements that does some three-dimensional stress states. I'm wondering if your shell element is good for sheet metal forming, and if it actually produces three-dimensional stress state or just plain stress. I noticed you verified it with continuum elements in Abacus and ANSYS, gained efficiency, which is great, but does it produce three-dimensional stress state? Thank you.
So I think, thank you for asking questions. Sometimes people don't realize that elements are used by different people for different things. So most of the linear analysis, no non-linearity. So Abacus ANSYS-like shell elements, they're okay, no problem. Because only when there is a large deformation, there can be problems not only locking, this so-called reduced integration, stabilization ideas that are artificial, they can create negative energy locally, okay? And the user doesn't know, okay? So they just look at the numbers and they don't even know if the numbers make sense, especially they don't know the real response of that particular problem, right? So they depend too much on the abacus and ANSYS-like. So what I'm trying to say is we need to help ANSYS abacus-like programs to improve their capabilities. That's all I'm saying. So when people use for large deformation, whether it's stamping or other kinds of structural analysis, they may have issues. By the way, one other thing, I think nobody builds things until they really do experiments. Okay? So they're not going to just because abacus predicted that they say, oh, this is good, I'm going to just depend on it. No. They actually want to see it. See, the certification of any structure component requires experiments. Okay? Crash test, drop test, all of these, right? So what are we trying to do? Reduce the amount of testing, that's all. We cannot replace the testing completely. So reduce the amount of testing because it's expensive. And also same time give the designer an opportunity to play with different configuration, different materials, different interactions, see what happens type thing. So that is where computational tools are very important. So, but the tool has to be robust in the sense, not only work for linear problems, but also work for non-linear problems, problems with couplings, different phenomena. So that is where my effort is to help abacus and ANSYS-like folks to improve their capabilities. And someday, for example, for a long time, Ted Belichko promoted the meshless methods, right? You remember that, all of you. There were sessions at every conference full of people. But what happened now? You never hear a session at any conference on meshless method. So what happened is, so the person who was promoting is gone from this face of this earth. And all those people who are on that bandwagon also deserted it. Because it was not able to compete with the traditional FEM. That's the key. Meshless methods cannot do the same kind of job as traditional FEM. If we can do it, then they would have adapted into commercial codes. Okay? And same thing is going to happen more or less with peridynamics, phase field, because they are not getting into commercial codes, because there is a lot of criticism from very well-known mechanicians that these are not physically consistent approaches. So what I'm trying to say is that we need to be more science-based people. Physics understanding is a key to our mathematical model development. And also all of the constitutive models have to be physically right, meaning all the parameters of the constitutive model has to be measurable. If you cannot measure those parameters, then you don't know anybody's game to introduce these parameters, right? So anyway, I don't want to take too much time to address. I hope I kind of answered your question, right? So I'm not saying don't use abacus or ANSYS. That's not my message, okay? I'm saying they have limitations. That's my message.
Thank you. Thank you very much, Professor Reddy. Somebody else? Okay, Professor Petkovic
in the back,
is also there. You can bring him the microphone.
Hi, since I come from the field of numerical analysis, I wanted to ask you just one specific question about higher order shell elements. How did you choose the interpolation order? You mentioned the 7th order element that you used in your simulations. How did you determine that order?
Right.
And do you have some recommendations on how to do that in general case?
Yeah, if I am able to hear you, how to determine the degree of interpolation, is that correct? Right? Okay, so I will give a very simple example. Think of a buffet versus, if you go to a restaurant, right, order by your choice or go to a buffet. So if multiple people who are hungry or big body, a thin body, right? So if you provide a buffet, the people eat according to their stomach, right? You understand what I'm saying? So the physical variables, displacement like compared to rotation like variables, if you say, for example, rotation variable should be only linear and displacement should be quadratic because du dx plus rotation variable is the shear strain. So if that is not going to match, if shear has to vanish, there is no way it will vanish, right? So whereas if you put both to be higher order, they will adjust according to the constraint, kinematic constraint they have. Okay? So the way you determine, you ask a very good question, practical question. In these problems that we did, we tried with p equal to 2, it didn't converge, then we went to p equal to 4 and p equal to 8. So it depends upon your actual kinematics or deformation that you are trying to represent. If it is only a shell with a small amount of deformation, then you don't need to go to p equal to 8. P equal to 2 probably will do it. Okay? So it is problem dependent in the sense what is the degree of deformation, complexity of kinematics of deformation. So that is how you determine. So there is no formula. Okay? Yes, there is no formula. But we found p equal to 2 is the minimum. If you go p equal to 1, it is going to lock. You will not be able to do the right thing. Okay? Thank you.
Thank you very much for your question. Also, I have one very short question. It's related to your first topic. I will try to be very short, but we can continue later because we are really a little bit in tight with the time. It's related to the 3D, this element. Did you test maybe the 7 parameters element for shell structures, for some structure which is possesses some deviation, or it's not fully symmetric, or it's a little bit different? This is good in these kind of things, because I already had the same problem, but in vibrations we did not calculate stress. In vibrations, when the structure possesses some kind of damage or notch or something like that, so we did not use HP version, finite element method, we used P version of finite element method. So I'm just interested in this. Did you test the element for some kind of structures, shell structures with some deviations? Nothing else. You can be very short and we can go shorter, or we can continue later. Right. Thank you, Professor.
Yeah, well, I think in short, you need to know the physics enough to be able to see. The people who do computations should not be forgetting the mechanics behind it, right? So whether the degree of interpolation or what is happening in a particular problem in terms of whether shear deformation is significant, right? So if it's thin shell structure, if it is large deformation, shear deformation will show up late, not in the beginning, because it is a higher order effect comes in through, especially if it is dynamics.
Yes,
okay?
I think
right.
Yes.
So I think these kinds of things cannot be just done as a rule of thumb or some generic rule that so use this many elements or this degree of interpolation. You have to know the specific problem and what is being experienced in terms of the modes of kinematic modes as well as constitutive model. Okay. By the way, in this equation we use the generalized Hooke's law, but generalized Hooke's law is between second Piola-Kirchhoff stress tensor and green strain tensor.
Yes.
But all of you know that second Piola-Kirchhoff stress tensor is mathematical. It's not physical. So you have to relate that to the Cauchy stress tensor, which is non-linear. relationship is non-linear. You will see totally different result for the Cauchy stress compared to second PL or Kirchhoff stress. And your failure is connected to the Cauchy stress tensor. Okay? Because it is physical. Physical failures are connected to physical measure of stress. Cannot be mathematical measure. Okay?
Yes.
So these are the kinds of things. I don't want to give the impression that I'm going somewhere else. I'm saying whatever is in the code, you have to understand in and out of what it means. So people routinely use, second PLR Kirchhoff stress tensor. Well, it is not mathematical. Okay?
Yes.
Okay, but it's not physics itself is there until you go to the Cauchy stress tensor. Okay.
Thank you, Professor. Yes, that's a question because ANSYS and Abacus they possess a lot of not mistakes but disadvantages.
Yeah, so
that's the main problem. So we already saw that, and this is some kind of continuation of the question of Professor Knežević, because we are making something in the basis, and then we would like to change the element or to increase the to decrease the degrees of freedom for analysis. Okay, Professor Reddy, thank you very much on the very end of this presentation.
Thank you.
This is a certificate of appreciation. Thank you very much for your excellent speech, for your presentation. Thank you very much. And one thing more, I have my personal gift. This is one book we published a few days ago. It's arrived from London, yes. Published with my colleagues, Professor Jan Deng and Professor Petkovic and colleague Ristic. It's published for Elsevier. It's very fresh, and we used your theory in most of chapters, so because of that it's related to this topic. It's not related as like a promotion. So please, this is our present for you. Thank you very much, Professor.
Okay, as I am chair of the next session, next plenary session, I will introduce myself to all of you that you don't know me. I'm Julijana Simonovic, and stepping here in this fora, I have a double role. I will use just wanting to draw attention for my first role here, and please don't mind me if I start with storytelling. You know all about storytelling, but I'm not going to tell you any fairy tale. It will be just a life story about trust and timely and efficient support. So, you all know about that life story. Okay, you are familiar, you know, and as you all know that I'm not going to deep down in the details. I just want to conclude with my deep appreciation to Professor Stojanovic, President of the Serbian Society of Mechanics. Thank you, Professor. I also want to take a second just to say thank you, Professor Chandra, the Secretary of the Society, that they actually trust in us and gave us their support to organize everything here and to meet you all today here. No, they were main organizers, but there would be nothing about this story if there were no logistics, and I have to say that because our scientific research organization, as we call them, our faculty support us logistically. Also, this scientific technology part support us. We are now here, and there would be nothing without all those guys, diligent guys and girls in this red shirt. They are very should I say, brave and diligent and dangerous also. So please be brave and ask them whatever you need in following 3 days. I hope you will be here for 3 days. They know everything about the organization, they know everything about the local area and everything. I'm one of them, so please ask me whatever you need. So that's my first role here. And now I am in the role of chairman of this plenary session. And so, ladies and gentlemen, my dear colleagues, thank you for your attendance here. And I have great honor to be to invite you to this plenary lecture at the 10th International Congress of Serbian Society of Mechanics. Today we are privileged to welcome one of the most distinguished scholars of theoretical and applied mechanics, Professor Rastko. And I'm going to tell you just another story, and it will be a live story about Professor Elishakov. So, Professor Elishakov is a distinguished research professor at Florida Atlantic University with over 50 years of experience and an extraordinary academic output, more than 620 scientific papers and 34 authored or edited books. And his work spans a wide range of scientific topics, including probabilistic and deterministic mechanics, stability, vibrations, nanotechnology, and composite materials. I hope Professor Elishakov agrees with me for all this huge amount of interest and insights. And here's a special note for all of us gathered here in Niš. And I want to draw your attention to one note that last year Professor Elishakov, with the similar topic that we have honored to listen here today, won prestigious in mechanics. Why do theoretical and experimental buckling laws of thin shells diverge so dramatically? And how can probabilistic approach help reconcile theory with practice? So, Professor Elishakov, I have a question. Can you please answer? And the floor is yours.
Good morning, ladies and gentlemen. I am just telling you that now is 11:50, so I cannot finish earlier than I must finish. So 11:50. Title is Resolution of 20th Century Conundrum in Theory of Elastic Stability. Hvala vam puno što ste me pozvali da održim. I would like to thank very much Professor Simic, Professor Stojanovic, Professor Simonovic for their most kind invitation. And we waited since year 780 when Serbia was established until we got here at the 10th International Congress. May there be many, many congresses of mechanics in Serbia. Okay, so that is this Congress. And look please, in 1744, Leonhard Euler gave us a gift. He gave a gift of buckling load of uniform column. By the way, Leonhard Euler was criticized. They said, come on, I did it, Moschenbroek said, and others. They did not like. Leonhard Euler responded, my theory is not only correct, but not unbeautiful. Next century, 18th century, was dedicated to decade of 20th century, buckling load shells. Buckling load shells. Cylindrical shells. However, cylindrical shells don't care about who was the first. Why? Because they don't care about who was the first. Now this problem, my dear friends, is super easy to solve for us. Okay. Why? Because this problem has a solution. W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha. Okay, because it's a free vibration. There is no loading. Now from W of 0 equals 0, we get A1 equals 0. Do you remember? Because K1 is not 0 at 0, it equals 1. The rest are 0. So when I substitute 0, I get A1 equals 0. Second derivative equals 0. You remember that first derivative of K3 equals K2. First derivative of K2 equals K1. So that means that A3 equals 0. Okay, A1 and A3 equals 0. Now this problem, my dear friends, is super easy to solve for us. Okay. Why? Because this problem has a solution. W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha. Okay, because it's a free vibration. There's no loading. Now from W of 0 equals 0, we get A1 equals 0. Do you remember? Because K1 is not 0 at 0, it equals 1. The rest are 0. So when I substitute 0, I get A1 equals 0. Second derivative equals 0. You remember that first derivative of K3 equals K2. First derivative of K2 equals K1. So that means that A3 equals 0. Okay, A1 and A3 equals 0. Now this problem, my dear friends, is super easy to solve for us. Okay. Why? Because this problem has a solution. W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha x. Okay, because it's a free vibration. There's no loading. Now from W of 0 equals 0, we get A1 equals 0. Do you remember? Because K1 is not 0 at 0, it equals 1. The rest are 0. So when I substitute 0, I get A1 equals 0. Second derivative equals 0. You remember that first derivative of K3 equals K2, first derivative of K2 equals K1. So that means that A3 equals 0. Okay, A1 and A3 equals 0. Why? Because this problem has a solution. W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha x. Okay, because it's a free vibration. There is no loading. Now from W of 0 equals 0, we get A1 equals 0. Do you remember? Because K1 is not 0 at 0, it equals 1. The rest are 0. So when I substitute 0, I get A1 equals 0. Second derivative equals 0. You remember that first derivative of K3 equals K2. First derivative of K2 equals K1. So that means, why? Because this problem has a solution. W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha x. Because it's a free vibration. There is no loading. Now from W of 0 equals 0, we get A1 equals 0. Remember, because K1 is not 0 at 0, it equals 1. The rest are 0. So when I substitute 0, I get A1 equals 0. Second derivative equals 0. Remember that first derivative of K3 equals 0.
Of numerous scientific meeting, also two Congress of Mechanics, and also numerous symposium, international symposium of nonlinear dynamics, nonlinear oscillation, not including some his books in publishing house Građevinska knjiga i also Zavod za izdavanje udžbenika in Serbia. But this information is very important because must to know that in this period books was published by not like this by PDF of computer, but very manual process for composing all order and also all pages, and then is very difficult, and this result is very important. Also, I say that at our chair of mechanics, numerous scientists from all the world was participated in our congresses and scientific meetings from all the world. But I wish to list some from Russian Federation, from some Republic of Russian Federation, and also for start this Irina Goryachova with his very short scientific description, CV, and this was our last meeting in Ufa. This is capital of Bashkir Republic. All Russian Federation Congress of Theoretical and Applied Mechanics, and Irina Goryachova was president of the Committee of Theoretical and Applied Mechanics in all Russian Federation. Our previous Congress in Niš was 1995, and one of plenary lecture was academician Felix Chernousko from Russia, and also Felix Chernousko was honor member of Serbian Society of Mechanics, and also member of technical department of Serbian Academy of Science and Art. Also, this is from Congress in Tara. You can see also Professor Hispanos from Rice University as a plenary lecture, and this is some participant of the lecture, Professor Academician Felix Chernousko, giving Serbian Academy of Science and Art. This is in our. This is very interesting photo from Orlando. I was organizer of one mini symposia, Integrity of Dynamical System, in Orlando at a big conference of nonlinear analysis involved, and then we can see Professor Lakshmikant Khan, president of this international IFNA. This is International Federation of Nonlinear Analysis. Professor Lela, his wife, Felix Chernousko, also very famous professor and academician Matrosov, who visited Serbia numerous times, one of the founder of this is from Niš, Professor Vitaly Vitalyevich Rumyantsev, academician, also president of, editor-in-chief of the journal Prikladnaya Matematika I Mehanika in Russia. This is Matrosov. This is Matrosov, and also academician Stanislav Vasiljev, one of director of Institut Problemi Upravljenja v Moskve one period, and also you can see one map. Name of Matrosov is named one body in mechanics. He last also academician of Serbian Academy of Science and Art, and numerous time visited Mathematical Institute Grade and some our international congress, Valery Kozlov, also a member of Serbian Society, Scientific Society of Serbia. Now I wish to announce lecture of my good friend, academician Irina Goryachova. Lecture of this plenary. Lecture is modeling. A lecture is modeling of contact, fracture contact, reinforced fracture mechanics of between deformable bodies, and also for in the case of friction.
Thank you very much, Professor Hedrick, for your introduction, and good afternoon, dear participants, dear colleagues and friends. It's my pleasure to be in Niš this year, and I would like to say many thanks to organizers of this conference and to President of the Serbian National Committee in Theoretical Applied Mechanics, Professor Simic, for invitation to come here. It is my great honor that I am here in Niš, not for the first time. I participated in the several congresses, Yugoslavian congresses in theoretical in applied mechanics. First one was in Portorož, and I met there Professor Viktor Salnikov, Professor Velika Vucic, and also I was at Zrnjačka Banja and in Niš in 1995, and met Professor Dragiša Nikadijevic and Dragan Zivkovic. And now I again in Niš, and I'm very happy. In my talk, I will tell you some problems of contact mechanics with application to tribology. And this, as you know, tribology studies studies the processes of friction and wear of materials. It's very important because we lose energy, we lose materials due to friction and wear. And we try to develop in the lab, which I'm a head of tribology lab in the Institute of Ishlinsky Institute of Problems and Mechanics, and we study to develop analytical approach to study tribological problems as well as experimental study some particular problems. And here I used for the presentation the problem of fatigue fracture of materials in contact interaction. So this is contents of my baby. I will not describe. I will describe each part during my presentation. So, due to cyclic loading of materials in friction process, the process of accumulation of fatigue damage near the surface takes place. And you can observe this phenomena when you look at the rail surface or wheel surface, and you see some damage spots at the surface, and they are deep enough. And so, due to this damage which we observe, but some of them we cannot observe because the damage accumulates under the surface. Due to this process, sometimes broken of rails takes place, and it's a very unwilling situation and very dangerous situation. So it's very important to create the model to predict this process. And this macro scale, it's only one example, because a lot of you can also tell me many other phenomena. For example, rolling bearings. It's also fatigue wear is very dangerous for this system. And micro scale, the cyclic deformation under surface takes place due to existence of microgeometry of contacting bodies, asperities. And asperities come in contact, asperity, and go out of contact, and then again, and we have damage accumulation in very, very thin layer of the surface, and particles come out of the surface. It's not so dangerous as in rails, but at the same time, due to in the duration of the process, there is essential, sometimes there is very essential wear, and also this part of the system cannot work further. So, what's the way to model this process? Of course, due to contact interaction, we have stress concentration, contact stress concentration in the contact zone, and also internal stress concentration near the in subsurface layers near the contact. It's very important to develop the methods to calculate the contact stresses, then internal stresses, and then to calculate the damage functions under the surface and predict what's happened in time during the contact interaction of different parts of tribal junction. I use, for example, the contact problem. Now we go to analytical study. I used as an example the problem of rolling contact of the ball, on the elastic ball, on the elastic half space. So this, as it was shown by Reynolds, in contact area, there are sub-areas where stick of the contacting bodies takes place, so the same velocities, velocities of deformation of two bodies, and slip zone, where there is slippage between contacted surface. So the boundary conditions, we formulate the boundary conditions in these two areas, sub-areas, subregions. In the subregion of stick subregion, it does not work. Pointer does not work, I think so. So in stick subregion, the shear stress less than limiting shear stress, which is coefficient of friction multiplied on contact pressure. I will use this one. Не работает она. No, let me the previous one. Yes. So contact conditions. Yes. Yes, I see. So this is conditions in slip zone. So shear stress less than coefficient of friction multiply on contact pressure. And it's too much contact pressure. And in slip zone, where this function, slip function, is not zero, we have limiting friction conditions in this subregion. So this contact condition, we formulated we use the variation approach, so formulated the sum functional, and minimizing this functional, we calculate the contact pressure and shear stress in stick and slip subregion. This is a famous method, and it was developed first by Kalker and then by other scientists. For example, here indicated the paper by Professor Goldstein and his co-authors. So using this method, we calculate the contact stresses. And here the different the result of calculation of contact stresses for different contact conditions. On the left-hand side, there is we calculated in the absence of surface layer, but sometimes, in particular in rail wheel contact, the friction modifiers of different with different properties are used. And in this case, we have intermediate layer, and for the intermediate layer, we have different character of contact pressure distribution and non-zero derivative at the end of contact zone. This is in rolling of contact, the middle picture, rolling contact on non-linear elastic surface layer, and with viscoelastic surface layer, we have some other picture also with non-linear, non-infinity derivative at the end of contact. So, the left-hand side is the absence of for identical materials. To calculate the shear stress, as I mentioned, we use the variational. We formulate write the variation function, and then minimizing this functional, we calculate the shear stress. Presented figures showed that there is stick zone where the value of shear stress less than a limited value, and slip zone. And also for stick and slip zone, it's possible to calculate based on this procedure. Also the displacement, relative displacement of contacting surface in these subregions. So we calculated contact stresses, and now, based on the contact stresses, calculate the internal stresses. And due to analytical approach, we used some dimensional parameters which explain or influence on the distribution of internal stresses under the surface. For example, here we calculation for different it's also interesting to study what is the effect of friction, value of friction coefficient. And also, I will not explain all the results, but you can see that the value of maximum value of principal shear stresses, as well as the depth where they have appears, depends essentially on the value of friction coefficient. And here on the left side, the function of maximum shear stress under the surface, principal shear stress under the surface as a function of depth for various values of relative slippage and friction coefficient, shows that there is two maximum the surface and under the immediate layer. I mentioned that it is model immediate layer. I mentioned that it is model of friction modifier. What's the influence on this, on the maximum of the principal shear stresses for different values of relative slippage and other contact conditions. So you see that based on the analytical models, it's possible to control the process of damage accumulations. For example, to use the friction modifier, to use the intermediate layer. Or if there is no intermediate layer, varying the friction coefficient, for example, we can choose the most appropriate situation for stress distribution in contact and internal stress distributions. But next, now we started stresses. But what's the influence of stresses on damage accumulations? So in cyclic loading, we have amplitude, some amplitude variations of stresses under the surface. So with maximum stresses and zero, for example, stresses, and so it's a very common approach that the rate of damage accumulation depends on the amplitude values of some stresses which control the damage accumulation process, stresses or von Mises stresses, and then to calculate the amplitude value of the stresses lower line in this slide, and this is the way to model damage accumulation in subsurface layers in contact interaction, cyclic contact interaction. For example, we used this approach to study the damage accumulated in the rails and take into account the changes of surface profile due to wear. And this is two competition processes. So wear process leads to change the wear profile, but changing the wear profile, we contribute to the damage accumulation process, because the function which we calculate the previous shape is we add to this function the function calculated from the new surface. So this is some process that sometimes wear can prevent wear of the contacting bodies, can prevent the damage accumulation and fatigue initiation of fatigue crack inside the bodies. We know the parameters which involve, which control the process, and we can then to find the best way to prevent the fatigue damage. Our calculation was compared, results of our calculations was compared with the method of initiation of surface cracks, which can be on the surface and under the surface. And the depth of cracks initiation was calculated from the model and from the tests were very in a good agreement and and predicted the same depth of crack initiation in this process. And what is, we know now, we understand now what is very important for accumulation and what can prevent the accumulation, damage accumulation process. We calculated with taking into account different values of residual stresses. You know that there is possible to create the residual stresses under the surface, for example, by laser treatment. So, and using the different regime of laser treatment, it's possible it's possible again, let's create some residual stresses under the surface, and they influence on the stress distribution under the surface and on the damage function. And all this damage function can be calculated analytically. And in analytical calculation, we use different kind of damage function, linear function calculations. There's also some numerical calculations, but based on the analytical model of two bodies of periodic shape coming into contact. And, but the main features of the process are the same as in the previous more simpler model. And characteristic of the Weir process, incubation period, unsteady state and steady state part of the process, it is the same. And what is interesting, based on this model at microscale, we can reduce the Weir equation, which usually not calculated but measured in the tests. But here, based on this model, it's possible to calculate the Weir equation, so dependence on the Weir rate, on nominal pressure, and sliding velocity. And based on this Weir calculation, this is the third line, we can formulate the mathematical analytical approach to study the kinetics of the Weir on macro scale. So to calculate the pressure distribution, shape of the one surface at different stage of the process at macro scale. During my presentation, I emphasize about the way to control the distribution of internal stresses and so the control the Weir process. And here some summation of the results. Maybe I will not read again this. I mentioned each of them during the lecture. So we can use the residual stresses, we can apply the we can use some intermediate layer between surfaces to control the process, and we can use microgeometry of contacting bodies as the parameter which control the process of wear and process of fatigue, fracture of contacting bodies in cyclic loading. And this is my young colleagues, which are PhD now, based on this research and other researchers. They passed their PhD thesis and work a lot, involved a lot in this problem, its development. But the other problems which we are interested in our laboratory, tribology laboratory of the Ishlinsky Institute for Problems in Mechanics, this is interaction of rough surfaces, effect of adhesion in contact interaction, lubricated contact theory, influence of material inhomogeneity and coatings in contact interaction, development of the computational methods of contact characteristics and friction forces in various joint, application to biological problems, results of contact mechanics results in biological problems, development of experimental methods, composite materials, and go to the microscale to see what's happened in contact interaction and microscale. Thank you very much for your attention. And I would like, and maybe you have any questions to me.
I would like to express my and also all participants of this conference for your lecture with very content new scientific results in very difficult problem about fracture in the situation of
contact interaction.
In
contact interaction,
friction and also in contact, because contact is very difficult problem, and you have numerous analytical result also in experimental. For beginning, I have one question. Can you make some comments about deformation energy around contact area between bodies, and when start fracture, which type of this fracture?
Okay, but you mean that in an energetic approach,
case.
Energetic approach, of course, for crack propagation, for example, we don't model now what in this results when I presented here. There is not model of crack propagation. There is model to only crack initiation. So but damage accumulation.
Fatigue of this fracture.
Fatigue damage. So cyclic, no homogeneous body, and fatigue appears. Fatigue damage appears in what point, but not crack development, crack initiation, crack development. We don't.
Propagation of
no propagation
in this area.
No, we don't. Now we stop here, but maybe then we will go
Thank you.
Later.
Any question from
in the head?
Participant? Are any questions? Discussion, comments? Lecture is open. Thank you. If not, Juliana say that I must to give this diploma for plenary lecture.
Thank you very much.
And also Juliana dođi i ti. Ne, dođi i ti ako treba da se slikamo.
Thank you.
Before we start a new session, I will first want to thanks to all plenary speakers and their impressive works and lectures. This session is for Rastko Stojanovic Award. We have two excellent young enthusiastic researchers in the field of mechanics, and I would like firstly to present assistant for Faculty of Mechanical Engineering in Niš, Dunja Milic, to present us her work, comparative vibration stability analysis of a complex moving object with two novel stabilities there.
Good afternoon. My name is actually now formally Dunja Miljković, but it was Milić up until recently. And today I'll present a paper titled Comparative Vibration Stability Analysis of Complex Moving Objects with Two Novel Stabilizers. Vibration of a vehicle that moves on a long elastic structure can become unstable due to elastic waves the vehicle itself generates in the structure. A typical example of such a vehicle is a high-speed train. When the train velocity exceeds the minimal phase velocity of the waves in the track structure, vibration and stability may occur due to excitation of anomalous Doppler waves known to produce a form of negative radiation damping. This type of instability not only amplifies the vibration of both the vehicle and the track, but also reduces passenger comfort, accelerates the track degradation, and can even increase the risk of the train derailment. In this research, the focus is on dynamic behavior and vibrational stability of complexly coupled moving oscillator that moves along a free-part, viscoelastically connected infinite beam foundation system, and special attention is given to the influence of additional stabilizer, where two different configurations of additional stabilizer are considered and compared. So first, as I said, the model consists of complexly interconnected moving oscillator. It moves along an infinite high-order deformable beam layer structure with flexible support that rests on viscoelastic foundation, where the rail is presented as a flexibly supported infinite beam, and both the slab and the concrete base are also presented as infinite beams, and the connection between the structure is presented with spring and damping elements. The equations that mathematically describe the interconnection within this infinity coupled layer is presented with these equations, where the notation used is in equations is presented below, and with P1 or 2 in the first equation is represented the response of the coupled moving oscillator, where P1 is for the first configuration that we are considering, and P2 is for the second configuration, and the full models that we are considering are presented here. In both models, the vehicle consists of a rigid bar that presents the car body. It is supported by two bogies by the secondary suspension, and it is and connection between the bogies and the truck structure is achieved through 4 wheel sets. Each wheel set consists of one wheel and primary suspension. The differences between these two models is in the way the additional stabilizer is connected with the coupled structure, where the first configuration is when the additional stabilizer is connected to the car body through the spring and damping element. It's presented in figure 4. And the second configuration is when the additional stabilizer is connected to the bogies. It is presented on the figure 5, and the reaction of the complex moving oscillator for both cases are presented here with P1 and P2, as I said. In the case of the stabilizer connected to the car body, the full form of dynamic equilibrium of the coupled moving oscillator can be described by adding these equations to the previously written equations that describe the foundation. And in the case of the stabilizer connected to the bogies, the full dynamic equilibrium can be described by adding these equations below. And I don't want to go on about this equations too much, but in both the notation that is used for both models is presented below, and with the K-ni and E-ni are presented, it's the last line, are the stiffnesses, modulus and damping factor of elastic coupling involving a stabilizer connected to the bogies, and with the K2 and E2 are presented the stiffness modulus and damping factor of the elastic connection involving a stabilizer connected to the car body. So now, by introducing a moving reference system up above, the equations, previously written equations can be rewritten, and the characteristic equations of vibration can be analyzed by applying the integral transform to the system of equations. The transforms are presented here, and the application of the transform results in the system of algebraic equations for both systems, for both models. And after using the inverse Fourier transformation of algebraic equation, and by setting the values that zeta is 1, zeta is d1, etc., we can obtain the two system of algebraic equation with respect to the Laplace displacements of the contact points. First is for the first model, and the second is for the second model. The existence of non-trivial solution for both models depends on the condition that the determinants of the matrices G1 and G2 satisfy the condition that they are equal to 0, and the stability of models is analyzed through an investigation of eigenvalues of characteristic equation. If at least one root of the characteristic equation has a positive real part, the vibration of the complex moving oscillator are unstable, and that's the criteria for determining the instability of vibration. So now the solution method and criteria of stability. In order to divide the parameter space of the model into regions with different number of unstable roots that are the stable and unstable zones, the decomposition method is employed, and as a complex variable K0 is considered, which is the stiffnesses of the primary suspension. By using the decomposition method, we can determine a relative variation of the number of unstable roots, however not the number itself. That can be achieved by applying the argument principle, and level of instability is determined according to the number of appeared unstable roots for each segment of primary suspension stiffnesses. And parameter analyses are performed for the supercritical case when the velocity of the complex moving oscillator is higher than the critical velocity. The whole procedure of determining the critical velocity is not here presented, but it can be seen in, it follows the procedure presented in the paper already published that's presented below. So first we are examining the model which involves the stabilizer connected to the car body. That connection is achieved through using a spring of stiffnesses K2 and a damping element of the coefficient E2, and the parameters that were varied in the study are presented in the table. First 5 cases are performed for the lower, sorry, I didn't mention, with MS in the table is presented the mass of the stabilizer, with M0 the mass of the car body, and with K1 and E1 are presented the stiffnesses and damping coefficients between the bogies and the car body that are actually the properties of the secondary suspension. So first 5 cases, as I said, are performed for the lower values of the car body, M0, and first 2 cases consider the influence of increasing the damping coefficient between of the connection between the stabilizer and the car body. Then there are 2 cases that considered, case 3 and 4, the influence of increasing the stiffnesses of this connection. And then the case 5 is the case where we are considering the influence of reducing the mass of the stabilizer. And then the following 5 cases are presented, actually follow the same variation pattern, but are performed for the higher mass of the car body. So first, here are presented the results for case 1 and 2. On the figures are presented the decomposition curves obtained for this case. And in the table we can see the change of the unstable roots between in the different ranges of the K0, the stiffnesses of the primary suspension, and the ranges that have the 0 unstable roots are the ones that are actually the stability regions. We can see, now I don't have the pointer here. Here is for the case 1. Between these two values of the K0 is the stability region, and for the case 2 it is between these two values. And those stability regions are presented with gray areas on the figures. We can conclude that by increasing the damping, the coefficient of the connection between the stabilizer and the car body, the stability region just has a slight shift toward the higher values of the K0s, stiffnesses of primary suspension, as we can see here. And we have the slight reduction of the stability region, but the change is not very big. Then we are considering the next two cases, the influence of increasing the stiffnesses of the connection between the stabilizer and the car body. And in this case, the shift of the stability region can also be noticed, but now the stiffness is a bit toward the lower values of the primary stiffnesses, and the stability region, there is a bit of increase in the stability region, but also the change is not very big. And the case 5 is the case when the stabilizer mass is reduced, and this is the case where is the broadest stability region compared to all the previous cases. But we can see from the first 5 cases that variation of the mass of the stabilizer and parameters of the connection between the stabilizer and car body doesn't greatly affect the stability region. So now we are considering all these variations for the higher values of the car body, higher values of the mass of the car body. And first, again, the increasing in damping coefficient between the connection of the stabilizer and the car body. We can also follow the same, in this case, the change also follows the same trend observed for the lighter car body, but the effect is a bit more pronounced. Since we have also the shift in the stability regions toward the higher values of the primary stiffnesses, and we also have a bit of the reduction in the stability region. Next is the case when the stabilizer is connected to twice caviar car body again, but now we are increasing the stiffnesses of this connection. And in this case, the stability regions remains almost the same. There is we can see the trend that is observed for the lighter car body, but the change is neglectable in this case. And the last case is the case 10. It is the case where we have the lower values of the mass of the stabilizer, but for the higher values of the mass of the car body. And this is definitely the broadest stability region compared to all previous cases. It extends beyond all previously considered stability regions, but definitely for the case when the stabilizer is connected to the car body, the change in the considered parameters doesn't affect greatly the stability regions. So next are the results presented for the second model. That's the model that involves the stabilizer connected to the bogies through the spring of stiffnesses K-Ni1 and K-Ni2 and damping coefficient E-Ni. The parameters that were varied are also listed in the table, and first we are considering the influence of increasing the damping parameter between the connection of the connection between the stabilizer and the bogies now. First for the lighter case, first for the lighter car body, then for the heavier car body, which are cases 3 and 4. Then case 5 and 6 consider the influence of increasing the stiffnesses of this connection and the variation of those stiffnesses. And the case 7 is where the mass of the stabilizer is reduced. So first, here are results for the case 1 and 2. We can see that by introducing the damping between the connection of the stabilizer and the bogies, which is case 2, compared to the case when there is no damping in this connection, which is case 1, we can see now significantly reduction in the stability region, since the stability region now we can see even on the figures that is smaller for the figure 17 than for the figure 16. So we can conclude that in this configuration, the variation of the damping of the connection has an influence of the system, and now we are considering the influence of increasing the damping of this connection, but now for the higher values of the car body. And in this case there is even a bigger reduction of the stability regions, and there is even one more instability region for the higher values of the primary stiffnesses, since we have one more instability regions with 6 unstable roots as presented in the table. So definitely the damping parameter of this connection influences greatly the stability of this configuration. Next are the results for increasing the stiffnesses of this connection, but we are for the heavier car bodies, and in this case the stability regions are not very much affected. There is quite a little change in the stability regions. And the last case considered is the case when the mass of the stabilizer is reduced, but the heavier car body is still considered. And in this case, we can see also that the stability regions is almost practically the same as in previous results. So it means that the mass of the stabilizer in this configuration doesn't greatly affect the stability regions. So this study analyzed the vibration stability of moving oscillator on continuous viscoelastic beam foundation system, comparing two configurations with additional stabilizer, one attached to the car body and other to the bogies. The characteristic equations were derived, and stability was assessed using the decomposition method and the argument principle. Results showed that attaching the stabilizer to the car body provides wider and more robust stability regions, even with significant change in system parameters. So we can change a lot of parameters of the connection, but the stability region remains the same. And in contrast, stabilizer connected to the bogies results in smaller and more sensitive stability regions, practically in heavier vehicle configuration. And that is all. Thank you for your attention.
Okay. It's okay. Thank you very much again, Madam Milic, for your very interesting presentation. I will now ask the audience for possible question.
You may want to mention in future lectures that Timoshenko was one of the first people who considered such problems, and he also applied to Belgrade University for the job. So he's a bit Serbian.
Yes, thank you for your comment. That's definitely worth mentioning.
Okay, thank you, Professor. Do we have more questions? Okay.
Thank you.
Now we have another young researcher work for Rastko Stojanovic award. The name of next presentations is Infragravity Waves by Theodor Vračica.
Hello everyone, thank you for attending, and today I'll be presenting the current topic of my work, which is on so-called infragravity waves. But before going into infragravity waves themselves, I will give a short overview of waves in general. Very nice artistic example of it you can see in right here. So, surface water waves are a well-known phenomena. They occur at the interface of water and the atmosphere, and they are primarily generated through wind forcing, with gravity being their primary restoring force. And for these reasons, they are often called wind or gravity waves, although the latter kind of dropped from use because now gravity waves are, something else usually, and they are of great importance in a number of physical processes, engineering applications, and you can actually use them as a proxy for, many other types of wave phenomena. For example, they have been used to simulate problems in optics. And here you can see example. So this shows how waves, in a sense, serve as an interface between oceans and the atmosphere, affecting exchange of all fluxes, but also albedo of the water surface as well as surface ice cover. And for these reasons, they have been extensively studied. All the way to Roman period, they definitely did take into account wave properties when they were designing their ports, harbors, etc. And at their most basic, they are simply a disturbance of water surface, or some of disturbances of water surface that is propagating in time and in space. And some of their, actually maybe their most fundamental property is dispersion relation, which relates frequency omega to wave number k, and you can see it on the bottom left. And through dispersion relation, you can determine c, propagation velocity of waves, and group velocity, which is the omega decay, which is the speed of energy propagation, which is not necessarily equal. And here you actually see, just sum of two waves propagating. And you can actually see that, the speed of wave propagation is different from energy propagation, and this property affects, many other properties. But, to really quantify wave fields is a very complicated task. So in nature, they are propagating, in all directions, all frequencies, and to really, quantify it, you have to kind of, give some statistical description. which in its waves is spectra, which is essentially a distribution of wave energy, which is proportional to square of amplitude in frequency. And all the way back to 60s, 70s of the last century, people more or less understood what is this relationship between wind speed, atmospheric kind of conditions and local wave conditions. But in oceans, you have many different processes. It's different time and spatial scales. Starting from tiny bubbles all the way to kind of El Nino kind of affected like really long-term motions. But if we limit our considerations to just wave-like motions, we can see here kind of in a sense spectra of the ocean. On really small scale, you have capillary waves all the way to tides and transtidal waves. And in a sense, infragravity waves, which you can see in the middle, kind of sit in a sense in a niche of a sort. So they are not directly generated by wind, but rather by other waves. And they kind of are also at the intersection where, gravity is the primary restoring force, for higher frequencies, and Coriolis force, which is primary restoring force for lower frequencies. But, I'll just mention this, that it's not, when someone mentions infragravity waves, it's not immediately obvious what they mean by that, because many, different definitions have been proposed, starting from, their generation mechanism, which, there can be many different mechanisms, to the nature of dispersion relation, but the most common one and the one that is used here is kind of frequency range, and here we define it as frequency range corresponding to wave periods of 30 to 300 seconds. And, at least in deep water, their amplitudes are very small. Typically, on the order of a few centimeters to 3 at most, I would say, in normal cases. Although in the near shore, there can be, far, far larger. And, here you can see that, compared to, this is actually measured infragravity wave spectra compared to, wind waves which occupy higher frequencies, they are indeed, far smaller. And, but, despite these small amplitudes, they have a number of remarkable properties that make them relevant in a huge number of processes. So, they can have wavelengths which are, from order of kilometers to order of tens of kilometers. They can propagate at velocities exceeding 100 meters per second. And, they are affected by underlying bathymetry of the oceans and can propagate transoceanic distances. And, practically wise, they have a number of important, effects. So, perhaps the most known is, their effect on sediment transport and flooding. So here you can see, this red line which kind of corresponds to infragravity wave modulation, which can increase chances of flooding. They affect results of satellite altimetry. So these are kind of satellites which measure the curvature and elevation of water surface, and these G waves can really mess up with the results. They affect harbor resonances. If wave penetrates into harbor and with specific length that resonates with the harbor, it can damage ships and tear rings and so on. And a good way to think of it is actually a guitar. If you play, a well-tuned guitar, it will, have a resonating sound which is amplified in its body. They can lead to breakage of ice sheets, and they produce seismic noise which is often called earth hum. So this is kind of when IG waves hit coastlines, they, due to stresses at the bottom, they generate this kind of hum that was kind of measured for very long time, decades, but only at the end of 20th century it was discovered that this is the reason for it. But despite all of these effects, IG waves remain in a sense kind of, there is a gap in how they are studied. So study of the oceans is standardized in a lot of ways. So when environmental agencies, groups, when they model oceans, there is usually kind of an agreement what quantities are, model how ocean is described. Then there are also international organizations with UN which defined what is the most cost-effective parameters that should be measured and what constitutes a good measurement. And to kind of address these gaps, a group was formed which is headed by Professor Jaron Toledo, and I guess co-headed by Vika Grigorieva, Gala Krish, Kristi Hegermiller, Susan Stoll-Hensel, and I guess myself. And besides, the six of us, there is around 20 to 30 other researchers that are participating in this initiative. And we are addressing several issues regarding IG waves, but I will only talk about theory modeling and measurements in this presentation. So the primary generation mechanism for IG waves is nonlinear subharmonic interactions in near shore. So there are in general two primary ways where how this can play out. So you have in a sense forced oscillations, which if you have two waves which are non-resonant, for example, they will just merely produce kind of modulation that is propagating with, so a bound wave, so-called bound wave. But if you have resonant conditions, you can have energy transfer to higher or lower frequencies, which is what we are interested in, I guess. And here you can see governing equations. You have first Laplace or continuity equation. Then you have two boundary conditions at the surface and one at the bottom. But I'll just mention that nonlinearity enters through surface boundary conditions. And the most simple way to consider this is you have two kind of simple sine wave solutions. When you multiply them, you have a wave at difference frequency, a bound wave at difference frequency, and you have simply two propagating waves. When you sum them up and take nonlinearity into account, you will see that you have this kind of bound motion in dashed line which represents infragravity wave. And typically in the near shore they are where which is the most energetic, let's say, method of generation of infragravity waves. You have a mild slope type equation, and you have let's say n different wave modes. They will all interact, where phi is velocity potential. They will all interact to transfer energy to lower mode as well, which is represented by these first terms on the left-hand side. Okay. It is typically, if you look at, wind waves, gravity waves, most of the energy is in free mode. But for infragravity waves, it is actually often that you have significant energy in both free, free mode, which follows the dispersion relation, and the bound mode, which is essentially a forcing by free waves. But you also have, which is unique to infragravity waves, you have edge waves. So water waves similar to light are refracted. So, for example, you are well known that when you look at underwater, the light is refracted. And similarly, the water waves are refracted by change of bathymetry, and you can have waves that are essentially trapped along coastlines, the so-called edge waves, due to refraction of rays by bathymetry. So you can see these waves propagate from deep to shallow water, and this is how it would practically look, more or less, and the x-axis represents the coastline, let's say. Now, in order to model this all on global scales, it's not really possible to use a mild slope equation, and especially since this is only one method of generation. There are many other proposed methods which can all have cumulatively, when you take them, significant effect. So it's necessary to give some kind of statistical description, and this is through a so-called wave action equation, n being the wave action. And the terms on the left-hand side essentially describe propagation of wave action through space, domain, as well as frequency, or rather wave number and directional domains. And on the right-hand side, you have a sum of source terms, which are essentially sinks and sources of action. So the major problem is that many of generation mechanisms are not implemented, and the whole problem still needs to be studied, and especially even theory is in most cases not well developed. And just mentioned that of course there are already some models, but they are of IG wave generation, but they are purely empirical, and they don't account for a lot of IG wave properties. And I think I will quickly go over the measurements part. So in order to develop all this new theory and modeling perspectives, it's very good idea to have something to check against, something to serve as a guide for initial conditions, and to kind of get a sense of what's a good description of reality. And the most common method of measuring IG wave was through pressure cells. It's by far the easiest method. You just drop something in the water, and pressure cells can be deployed all the way to 10 kilometers all the way to the bottom of the ocean. And I'll just mention that the pressure response of waves can be in a linear case described like this, where this function k decays with the vertical coordinate, but because IG waves can have wavelengths that are tens of kilometers, they still can, pressure disturbance can still reach the ocean bottom. It's also a question of how do we quantify what we measure, and typically this is simply done through a so-called significant wave height, which is proportional to square root of total energy in this frequency range. Now the main problem with this approach is that it's not really possible to determine the directional properties or actually the nature of dispersion relations you have. You have free, bound and edge modes, and you can't really deduce which is which just from single point measurements. but it can be useful to actually derive kind of climatology of IG wave energy. It was actually done some time ago. And more recently, people have been proposing alternative methods. So sonic devices called ADCPs can actually measure full profile of velocity from which you can determine IG wave properties. And an array of pressure cells can be actually utilized to similar effect. Here you can actually see one example where a lot of pressure cells was deployed and their data was used to successfully determine IG wave properties. And here you can see an example of ADCP, which essentially emits sonic beams which are reflected back from impurities in the water, and these reflections are used to estimate velocities. And here you can just see an example of deployment at, I believe, 50-meter depth. And I'll just mention that in ice-covered seas you can have different, actually you have to have different means of measurement, and the motion of ice itself actually is used to determine wave properties. And for this purpose many different instruments from meters which are deployed directly on ice all the way to satellites have been utilized. And here finally you can see an example of actually waves propagating all the way from northern coast of I think even Alaska all the way to Ross ice shelf in the Antarctica, which was actually measured by a tilt-meter array that was deployed on ice itself. Here you can kind of see these in the bottom left, kind of these lines which correspond to observed islets. And essentially one of the main goals of the initiative is to apply to extend definition of one of the essential ocean variables, which is kind of done by one of the organizations that we mentioned. And we hope to include definitions of what is a good measurement, to propose what new techniques can be used, what new instruments can be used. And in addition to all of this, we are currently writing a review paper in which, besides modeling, theory, measurements, we also hope to cover data, both in storing it, reading it, accessing it, as well as data-driven solutions, lab experiments. This is to conclude. We hope to find new ways to measure IG waves, build a new framework within which the results are analyzed, and to drive new research forward. We hope to answer many of the theoretical questions that still remain, and to hopefully drive kind of community efforts on this topic. And finally I would like to thank now actually ended old project Magic, as well as IUGG for funding the work of this group. And with that, I thank you for your attention.
Are they good or bad for us?
Well, usually bad. My two main topics.
Professor?